Let's take a look at one more example of Pthreads programming. One of the issues with the shared variables that we've been using so far, in the last example we looked at a shared variable that kept track of a global minimum. Every time you lock a mutex, it's going to take some amount of time. There's going to be some additional overhead associated with doing that lock. And if we can avoid doing that, we may well be able to improve the performance of our parallel algorithms. And I wanted to illustrate that idea here with another kind of similar example that involves using another Pthreads API function called trylock. The difference is that the trylock API function will attempt to get the lock, and if it succeeds in getting the lock, everything proceeds as it has previously. But if it fails to get the lock, if some other thread already holds that lock, trylock is just going to return right away back to the caller. And what we're going to do, rather than sitting around waiting for that lock to open up every time we want to update that global value, we're going to just keep track of the fact that we tried and failed and just continue doing useful work. And then the next time we actually manage to acquire that global lock, we'll update it appropriately based on the information that we've kept track of until we've had a chance to update the global lock. What we'll see is that by reducing the amount of time we spend contending for that shared resource, the more useful work we can get done, and the shorter our parallel runtime is going to become. We're going to get better utilization of the underlying hardware, which is what we talked about previously as better efficiency, and that's going to be driven by lower parallel runtimes and higher speedups. And we're just going to use a very simplified kind of problem that we're going to try to solve here. The idea would be that we have some set of application-specific data in memory. It might be samples from sensors, it might be business information that's been read in from a database. Wherever that comes from, we're going to have this collection of records that are stored in an array in memory, and we want to process those records in some way, and then in order to achieve a speed up, we're going to give a subset of that array of records to each of the processors or each of the threads, and then run them simultaneously. So here's just the really super simple structure that I've defined. I've called it record T, and all it's got in it is just this single integer value. And here's where we would put the rest of our application data if we were doing a real application. The idea here is that I'm going to have a single value in there, and what I want to do is search for the number of instances of a particular value in that record. So you might think of this as like if you had a very large collection of records from, say, a database, and you were trying to find all of the sales that were completed in a particular region, and that region was identified by a numeric value, this would be a way to sort of do a parallel search across all your data, giving a subset of the data to each of the threads and looking for a particular value in parallel, and then you might do some other processing based on those things. Now, I don't have any real processing to do here on this fake data set, but I also want to represent the time taken to do some useful work. And again, this is just a kind of a preliminary example, so I'm not really going to do any useful work, but I would like to be able to see that there's some time spent every time we find the record of interest. In other words, every time we find a record that has the value we're looking for, we're going to simulate doing some actual work. And the way I'm going to do that is by using this standard library call. The U is intended to be a prefix for micro, so this is called the micro sleep function. You might have been familiar with the sleep libc call that says sleep this process, pause it for some number of seconds. The micro sleep actually has a much finer grained clock, so it's going to stop for some number of microseconds, so 1,000 microseconds. The idea is that when we find one of these matching records, we're just going to sleep for 1,000 microseconds and then continue on our way. So this is just intended to kind of simulate actual work, as opposed to work that we're going to, as opposed to time spent doing things that are overhead due to the fact that we're parallelizing this algorithm. We want to be able to distinguish between those two things. So just to make this simple, I've defined a constant called fake work that I'm going to use to pause the processing. Okay, so there's our simple fake mock application data structure. One of the things that we're going to want to do is check to see if we have found a record of interest, and I'm going to do that by just calling this little function called records match. So this takes 2 pointers to those record T structures, and it just looks to see if the value from one matches the value of the other. Again, this would be a more elaborate algorithm potentially to check for a whole bunch of criteria to say, hey, yeah, go ahead and process this record or not. But here all we're going to do is just check for a match. And notice that because I'm passing in pointers to these structures, I'm using the arrow operator on those pointers to fish out the value element of the structure in order to compare them. All right. This is the structure that's similar to the previous example, where I've defined something that I'm going to pass into each thread to tell that thread what to work on. As before, I've got a thread ID that I'm just going to use a sequence number starting from 0 to identify the threads. I'm going to have a pointer to a record T that is the first record that I want this particular thread to process. So this is exactly the same strategy as in the minimization algorithm, except now instead of pointing to an array of integers, I'm pointing to an array of record T's. I'm also going to pass along the count, how many of those records I want that thread to process. And then I'm also going to pass an additional record T pointer that is kind of the target record that I'm searching for. So as I'm walking down this list of records pointed to by start, I'm going to call this records match function on each of those records in the array and compare that with the target record. And if I find that target record, I'm going to say, okay, I've got a match. I'm going to do work, in which case I'm just going to call that micro sleep function we saw up above. And if I don't have a match, I'm just going to go to the next thing. Okay. We've got another mutex here that is going to be used to control access to this global variable called match count. And at the end of the process, what I want to do is have match count set to the number of records in my original array that match a particular value. The next function here, which we'll come back to and camp out on, is the thread start function. So that's the thing that's going to run in parallel, but let's just kind of cover the rest of the bases here. I'm going to generate some random values here for the value in that record T structure. So that's what that function does. And then here, kind of familiar now, we've got our pthread T array, which is just the bookkeeping information about each thread. I've got that thread args T that we just looked at up above, which is the parameters that I'm going to pass into each of the threads so they can know what work to do. I've got an array of all of the records. So again, this is just something I'm going to initialize to some random values, but this would be something that you might have read in from a database or from some other data source. I've also got a target record. So this is the record that I want to look for. And this syntax might not be totally familiar to you. If we have a structure like record T, we can actually initialize the elements of that structure by enclosing a comma-separated list of values enclosed in curly braces like this. So that target, let me bring up the target record again. So that's the shape of that thing. It's only got one attribute right now, which isn't very interesting, but that means that we can initialize one of those things by just creating a constant enclosed in these curly braces, and that will initialize this single target record to have a value equal to 7. And I just chose that arbitrarily because, and I know that it's in range of the values that I'm going to generate for values in those records. One of the challenges of making sure that your parallel code is doing the right thing is trying to figure out some way of coming up with a way to check to see, at least in a simple base case, that you're getting the answers that you expected. And in this case, since I'm basically searching through all these records to find ones whose value matches the target record, this guy here, as I'm creating that list of sample data, I'm going to count the number of times I randomly generate something that matches the target so that I can compare at the end of the parallel execution to make sure that the parallel version of the search came up with the right number at the end of processing. So expected count is just going to be the number I expect to see. I'm going to initialize these records. So again, we're going to seed the random number generator from the current time so that it's completely arbitrary. And then I guess I didn't show you these constants. So I've got a num records of 48,000. So I'm going to search through 48,000 records. I'm going to do that on 8 threads. And then that means that the number of records per thread is just the quotient of those two values. And I'll just use these constants elsewhere in the code. Notice that I'm kind of picking nice values here, right? Because 48,000 is an even multiple of 8, so the number of records per thread is an even integer value. That's not necessarily going to be the case in a real algorithm, but rather than try to monkey with that in this example, I just decided to do something where everything lined up nicely. So I'm going to initialize this list of records. I've already declared it here, record T, records of 48,000 records. And I'm going to iterate through that, and I'm going to take and assign the value attribute of the ith record to a random number between 1 and 10. And again, I've chosen a target value that's in that same range so that I very likely will have some matches. And I'm going to, again, in order to figure out whether the parallel version is working properly, I'm going to come up with a number of matches that I expect to have. So I'm going to call that same records match structure that I defined up here, and I'm going to hand it the record that I just generated and the target record. And if those two values happen to have the same value per property, then I'm going to bump my expected count so that at the end of the process here, after I run this in parallel, I can make sure that the total coming back from the parallel threads generated the right value. Notice here, again, just to kind of explain the pointer stuff a little bit more clearly, I have the records match takes pointers to those records, right? That's the way it's written with the arrow and stuff. So for the second argument, which is sort of the easiest to understand, I'm just passing the address of that target record, and the target record is just a record T, right? So I've got a pointer to a record T. And then for the first argument, records itself is an array, so that's a pointer, but I want to refer to the address of the ith record, right? The one that I just set a value for. So I'm going to say records of I, which is going to give me one of those records, and then I've got to get the address of that record to pass into records match so that I have a record T pointer for that first argument. So when I get to here, what I've got now is a target record that I'm searching for. I've got the list of records in my records array that have initialized to, again, just random values at this point, but could well be data from a database or something. And I know how many of the target record I expect to find in the data because I'm cheating as I build that up. Again, super great way to verify that your parallel code is doing the right thing, to just come up with some way to fake it into giving you a value that you know is correct. Okay, I'm going to initialize the mutex as we've done previously, so I'm just calling the pthread mutex init on that match count mutex, which we had defined up here, match count mutex at the top. And then, so next we want to fire up the individual threads. So as before, or as with the list minimization thing, I'm going to keep a pointer to a record T and just initialize it to the beginning of that array, and then I'm going to allocate a chunk of those to each of the threads. So this should look very familiar to you based on the last example. I'm initializing the thread ID. I point the start pointer to the beginning of the group I'm working on. Then I set the count to the number of records per thread, and that back up here at the top was just calculated based on the quotient of the records and the threads. And then I'm also, and this is a little bit different from the list minimization example, I'm passing in the record that I'm searching for in the partition of that overall array that's handed to each thread, because the thread needs to be able to figure that out. And then I'm going to call pthread create. So again, we're passing in the address of that thread, or the pthread T structure. That's kind of the bookkeeping about what's up with each thread. We're not passing any kind of customization attributes to the newly created thread. Here's our start function, find matches, and we're passing in the thread args of I based on the current thread that we're spinning up. And again, we have to pass an address of this structure to the start function. And because the start function's parameter is because the pthread creates parameter is defined to be a void star here, we're just putting in a cast to make this pointer look like a void star so that the compiler is happy. And then we increment the pointer to the next group of records in our original list. Again, because next group is a pointer to a record T, when we do this increment operator, it's now doing pointer arithmetic. It's not going to just add 1 to next group to point to the next byte. It's going to advance next group by the number of records per thread times the size of each record, right? So whatever that size is, and in principle we don't really need to know what it is because we're using size of here, or the pointer arithmetic will use size of. But however big this is, that number of bytes will be multiplied times this value, the number of records per thread, and that's how far next group will advance in memory. So it'll skip num records per thread records, not num records per thread bytes, but num records per thread records to set the proper value for the next thread that we're going to create. So same basic idea as the list minimization example, but now we're advancing our pointer by by some number of records instead of some number of integers. But same idea. Pointer arithmetic, when you add a value to a pointer, it's that many things times the size of the thing pointed to. And in this case, that's one of these record T structures. Okay, so that's going to kick the threads off to do their thing. And the next thing that the main thread is going to do basically is just wait for all the threads to be done. So again, we iterate over the threads. We use pthread join and use that threads bookkeeping structure and look for the termination of the ith element of that array, and then we're done. And then finally, we're going to just do some output here at the end. And at the end of the process, the threads will have updated this global match count variable, right? In a similar way to the way that list minimization did its thing. And if the match count that came from the threads corresponds to the expected count that we calculated as we were initializing the data, we'll say, hey, matched so many records as expected, otherwise matched so many records and it didn't work. Okay. So the interesting part that remains is the function that's run by all the threads, and that's this find matches function. So it takes this list of thread arguments, and just as before, because the pthread create function expects this to be a pointer to a function that takes a void star as an argument and returns a void star as its value, we have to do a little bit of hoop jumping here to coerce our data into the appropriate format and keep the compiler happy. So the same kind of thing happening here, where I'm going to cast that void star that I passed into this, or that pthread create passed into this, and I'm going to cast it as a pointer to the thread arg structure so that I can access the individual elements of that thread arg structure through this thread arg's T pointer. Okay, so that's just coercing the void star into a thread arg's T star, so I can use my handy structure up here. And then I've got some output here printing out the details of what I'm being asked to do here. So %d is going to be my thread ID. So that'll just print out 0 through however many threads I have. And then it'll print the address of the beginning of the portion of the data that I'm processing and the number of elements that I'm going to work on within this thread. Okay. Now, the point of this whole exercise is to illustrate how we can reduce overhead due to locking by locking less often than we have been in the past. But I want to, again, this is an empirical sort of thing. I would like to be able to run some experiments that actually tell me how much faster or slower one version of the algorithm is over the other. And then through repeated experimentation and tweaking and changing algorithms and so forth, we hopefully can arrive at the fastest possible parallelization that we know how to do for a particular problem. So the base values here, kind of the base case, is going to just be, let's just lock every time. And that's what I've got here in this for statement. So what I'm saying here is I'm going to have this index I, and I'm just going to iterate over all the records that I'm responsible for, that this thread is supposed to deal with. And I'm going to check to see if I've got a match, and if I do, I'm going to wait for a lock, update the counter, and then go back. So the operation that I want to do to check to see if I've got a match for the ith value of those records that I'm responsible for is calling this same records match function, and I'm passing in the address of the ith element of the array that I've been given. And I'm comparing that against the target that I was passed from the main function. So this thing is going to be non-zero or true if the value of the record that I'm looking at right now, the ith record that I'm responsible for, matches the target record. And if I do get a match like that, I'm going to always lock the mutex. And again, I have to just pass in the pointer to that mutex structure. And then I'm going to increment the match count because I'm ultimately trying to figure out how many records match. Here's where I call that microsleep function. So this is just going to wait for a millisecond to simulate something actually being done on this record, right? I've found the match. I've found a record that I want to pay attention to. There's going to be some real work that goes on in that match, in that matched record. You know, summing up some statistics for sales data, or who knows what it is. But I just want to simulate some actual time spent doing application-specific stuff, in addition to the parallel overhead associated with doing this in multiple threads. And then once that's done, I'm going to unlock the mutex. Okay. Let me go back to this function call. This might look a little scary here. Remember that this args pointer is a pointer to one of these guys, right? And that's what's passed in from the main function. So args and then start is just a pointer to this member of that structure, right? It's the pointer to the beginning of that portion of the original array that this thread is supposed to be dealing with. So when we say args of start, we're just getting to the array, and then when we say start of I, now that's telling me, or that's giving me the ith record in our subset of the array. And again, the records match function takes pointers to two of those records. So once I've fished out the ith value, I want to return its address so that I can use that to point to a particular record that's going to be matched. And then I've already got a pointer because arg's target is a pointer to a record. So that's already a pointer to the target record. And at that point, then I have two pointers that I can pass to records match, and that's exactly what it's expecting, right? A pointer to the first record, a pointer to the second record, and it's just going to compare to see if both records have the same value. If they do, I've got a match. All right. One odd thing here that you might not be super familiar with is the use of sharp if. Again, this is a preprocessor directive, so it's handled before the compiler even gets into the picture. But in addition to doing things like sharp defines and that kind of stuff, includes the preprocessor lets you conditionally compile code, conditionally include code in the resulting object file. And that's what's going on here. I want to be able to try this approach with locking on every access to that shared variable. And I also want to try to use the try lock to try to optimize the overhead due to locking. So I've got up here at the top a sharp define called always lock, and I've set that to a true value, right? A non-zero value in C is always true. So if I compile this code in this current state, it's going to include the code from this sharp if to just before the sharp else. If I went and redefined that always lock to be false, then it would skip over this code from the if to the else, And instead, it would compile the code from the else down to this end if. Okay, so this is a really common way of conditionally including code in your C programs, and it also is used a lot, again, in sort of empirical computer science when you want to compare one behavior to another, right? Rather than having to rewrite this whole thing or have a bunch of copies of things or link in a bunch of crazy stuff. This isn't a super elegant way to do this, but it works just fine. And as long as you're not trying to run 10 different combinations of code, which would, this would kind of become a nightmare at that point, and there's other strategies that we might employ to be able to access more than just a couple of variants. This is a perfectly acceptable way to do that. So when we come to want to do the evaluation of the version of this code that doesn't always lock, but uses the try lock, we just have to go in there and change that sharp define to make always lock be false or 0, and then recompile. And in that case, this block of code that we see here on the screen is what's going to be compiled in, and the other one will be skipped entirely. Okay, so let's take a look at what we've got going on here. The idea, in order to avoid having to wait for that lock every time we want to update the global count, what we're going to do is keep a local counter. So I've called that local matches and initialized it to 0. And what we're going to do every time we find a match, instead of locking and waiting no matter what, we're going to use a different Pthread API call. So here's the Pthread mutex try lock. It still works with a mutex object. So this is the same match count mutex that we've been using so far. The difference is if the lock is already locked, try lock will just return right away. Remember, if we called pthread mutex lock and the mutex is locked by another thread, our process will block, and we won't be able to do anything while that thread is blocked. So we're basically just wasting CPU resources. We're just sitting there twiddling our thumbs, waiting for another thread to unlock that lock so we can get in and do our thing. Try lock allows us to circumvent that. So if some other thread happens to be holding this match count mutex in a locked state, pthread mutex try lock is just going to return immediately, and it's going to tell us, is that thread locked or not? And of course it does that with its return value. So if pthread mutex try lock returns a 0, which as we discussed already, a 0 from these pthread API calls usually means it worked right. So in that case, we're saying we did get the lock. What we're going to do is we're going to update that global match count. That's the thing that's being protected by match count mutex. We're going to simulate some fake work, and then we're going to go ahead and unlock the mutex. Okay. Now, the unlock, you can see that we're using this with try lock. We've also used unlock with just plain old lock. And that's just fine. The unlock will unlock the lock that you're holding, whether you got it from a try lock that succeeded or from an ordinary lock after waiting for the lock to be released. Now, we haven't really said much here about this local matches variable, but the idea here is that we're going to keep track of how many times we've matched within our local threads portion of the original array, how many records we've matched. And anytime that we can get access to the global count of matches, we're going to update that global count with the number of matches that we've matched so far. So we might actually add 1 to the global match count. We might actually add a lot more than 1 to the global match count if it's been a while since our thread has been able to acquire the lock on the global match. So when we see the match comparison here is exactly the same as in the case where we're always locking. But when we do get a match, we're not trying to update the global count directly. We're just keeping track of our own local count of matches within this thread. Then when we do succeed in getting the lock, we're going to add that local count to the global count before we release the lock back to other threads. And then we're going to reset our local count back to 0. Now we might go for quite a lot of iterations through this for loop, coming up with matching records and failing to acquire the lock again which means that local matches is going to continue to increment as we keep doing useful work. And then eventually, when we do get the lock, we'll be able to add that local total to the overall total, and then go back to looking for more matches. Okay, so that's kind of the key thing here with regard to avoiding having to spend a bunch of time spinning on that lock. If the lock's not available, no worries, let's go on and try another record. If the lock is available at this particular moment, great, let's update the global total right now, reset our local counter, and go back about our business. It's important to note here that the match count variable, right, which we declared up here near the top of the code, that's a static data variable. It's allocated in that static data space in the process, and there's a single one of those that's available to every single thread, right? Everybody shares that value. That's how we can end up with a global total in that value. On the other hand, this local match count is local to our thread, right? It's an automatic variable, a local variable within the find matches function, right? Within this guy, which means that every thread is going to have its own copy of that, because automatic variables or local variables are always allocated on the stack, and each thread gets its own stack after it gets started by pthread create. So we can make changes to local matches all day long within our thread, and no other thread is going to have access to that value, and we're not going to be messing with any other thread. We only have to worry about locking when we're trying to update the global match count, this guy. Okay, the other thing that I'm doing here, and this is just purely for our ability to kind of understand and verify that the algorithm is running correctly, is I'm keeping a count of the number of times that I go try to get the lock and fail. So busy count, another local variable, 1 per thread. If the pthread try lock fails, in other words, I can't get the lock right now, well, I can't go ahead and update the global value that's protected by that mutex. Instead, I'm just going to indicate, hey, I tried once and it didn't work, and then I'm going to continue to go back about my business executing this for loop looking for more matches until such time as I can actually get the lock, and then I'll update it as I've just described. So in a way, that busy count gives us a kind of a metric to say how many times did you try to get this lock and you failed, and that would connect directly to the number of times that if we weren't using this try lock mechanism, the number of times that I got a busy count incremented because I couldn't get the lock would correspond to basically the number of times that this algorithm would just be sitting around doing nothing, right? It's just waiting for the lock. So it kind of gives us a measure of how painful it is to wait for the lock to be released. Now, if this was all we did, we would get the wrong answer for the total number of matches, because some of the matches are going to be here stored in that local match variable, and it might be that I get to the end of this list of records that I'm responsible for without having a chance to update the global match count with all of my local matches, which means I'm going to come up short on the number of matches that I should get. So at the end of that process of doing most of the matching, and I can see I print out the number of times I found a busy lock, if I have some matches that have not yet been added to the global total because I ran off the end of this for loop before I had a chance to get the lock and update the global total, I'm now going to be forced to actually do a blocking lock on that mutex. So I have no choice but to lock at this point. So this isn't a try lock, it's just a regular lock. If there's other threads in there, boo-hoo, I got to wait in order to update the global total, or I'm going to have a wrong answer. So I wait for the lock, I do the same operation, right? No, local matches could be 1, it could be 100. I want to add all of those local matches to the global count and then unlock the mutex so that other threads that are finishing up can get in there as well. And then I'm finally, at the end of this thread, I'm just returning null because there's nothing really I need to send back to the main thread. The only interesting information that I've got is that total match count, which would already have been updated before each of the threads return. And then I go back down here and the pthread join picks up a value that I'm just ignoring. I'm passing in a null pointer here for the parameter that would normally harvest the value that came back from each thread, because I don't care what the thread is sending back. I'm not sending anything back. And then I print out the values. Okay, so let's start by, so we've got this always lock value turned on. And again, that means that we're going to end up, if we compile this right now, we're going to get that block of code. Just go lock every single time. So let me show you the output here. Let me get to a shell. And I'm going to just, for yucks, do a make try lock to make sure that it's compiled currently. You can see that I'm using the W all and the W error flags. Again, W all says make every warning count. Pay attention to everything that you know about that could possibly be a warning, and generate a warning. So it's kind of dialing the warnings up to 11. And then W error says treat all warnings as errors, which means that if there's any kind of an error, if there's any kind of a warning, it's going to be treated as an error, and the compiler isn't going to generate any output in that run of the compiler. So I would really strongly encourage you to use both of those compile time flags when you're doing this, because it's going to chase out every last little weird thing in your source code that the compiler can possibly help you with. And if you got a clean compile that way, you have just a whole lot more confidence that you're not just sort of, I got an ampersand in the wrong place, or I've got a star in the wrong place. When we're dealing with structures and pointers and all those sorts of things, rely on the compiler to help you get everything correct. All right, so let's run this guy, and we can see that we get that initial output. Let's go find that. There's the in the find matches function, right, our thread function, we printed out our thread ID, the address of the beginning of the records that we're processing, and then the total number of records that we're responsible for. And you can see that each of the threads from 0 through 7, I'm running, as I showed you before, I'm running 8 threads here, so I should expect to see that many lines of output showing up. I get that information about which thread dealt with what part of memory. If you wanted to, you could sort of go back and figure out what's the size of each of those records, how many bytes are occupied by 6,000 of those records that have been allocated to each thread, and sort of verify that these addresses step forward in memory by the appropriate number of bytes. But at the end of the day, what I'm going to see here coming back from that is this output, right? Matched something or other as expected. So this 4675 represents the number of times out of the 48,000 records that I created randomly. That's the number of times that they match that expected record with a value of 7. Okay. Now that's interesting to see that it actually works. But one way we can go about trying to figure out how long this ran and what our performance was. I showed you an example previously where you can actually put in your code some timing functions that let you report how long things ran. You can get a kind of a rough and ready estimate of those things by actually just using the Unix time command. So time is a little bit weird in the sense that it is a kind of a prefix for other commands. And I'll just do an ls here. And you can see I get the output from ls as you normally expect, and then these new lines here show up at the end that you don't see, right? If I just do ls, I get that. If I do time ls, I get this additional info. This says that this is the amount of time it took for that command to run. So the real time basically corresponds to the wall clock time, right? How many seconds? In this case, it's just 3 milliseconds. I took 3 milliseconds of elapsed real time to run that command. The user amount here is actually the amount of time that the program is running in user space as opposed to in kernel space. So it's running the ls command proper, not any of like the system calls that the ls command might have requested, like a read from disk or whatever, which of course it did here and to do the ls. And then the sys is the portion that is dedicated to running inside the operating system kernel itself, essentially. So that can be a really handy way to measure performance of these things. So I'm going to go back to that try lock, and I'm going to put in a time prefix. Now we're running it again, and we got to kind of sit and twiddle our thumbs and stuff. This is kind of the nature of doing parallel programming when you're trying to do the experimental evaluation. And you can see here that we spent, on the real-time clock, we spent 5.8 seconds running that parallel program. Is that good? Is that bad? Well, We don't know. It's all kind of relative to some other numbers. But now we have a data point. We know that on eight threads, using a lock on every single access to that global variable, we took 5.8 seconds to run this thing. All right, now let's go back here into the source code and we'll shut that locking off. So with always lock set to 0, we're no longer compiling in this code that locks every time. We're leaving that out and we're compiling in this code that uses try-lock to check to see if it can actually update the global value, and only forces that at the very end here when it needs to store additional counts into the global variable. So we got to make sure we remember to compile. So I've got a make file here, so I'm just going to run make of try-lock. That doesn't seem right because I didn't save my file out to disk. There we go. Now we have a compile, and then we can run try-lock. Now I want to, this is just kind of a freebie here about how to use the shell for this kind of stuff. As you can see, I forgot to save my file, which is a bad thing. But sometimes what you'll find as you're running these experiments, repeatedly as you're doing development of a parallel algorithm or trying to characterize its behavior with different numbers of processors and stuff, you'll find that you'll forget to do the compile. So what I normally do is I will say make try-lock, and then I can separate that from the next command with double ampersands, and then I can say try-lock. What the double ampersands do is it's sort of the shell's equivalent of a logical AND operator in a C program. It basically says run this first command, and if it works, go ahead and run the next command. On the other hand, if this first command fails, then just stop there. So for example, if I go in here and I just put an intentional error in my code and then run that, it's going to go, oops, sorry, running the compiler had a bunch of problems, and then it doesn't do the run. But if the compile works cleanly, then that command is going to first do the compile, and then it's just going to go ahead and run the code. So this is what I almost always will do when I'm doing experiments like this, is I'll create that little simple command line structure that recompiles no matter what. And if it's already recompiled, there's nothing for it to do. It doesn't take any extra time at all, really. And then it'll just run the compiled code. But you're never, sort of stuck thinking to yourself, did those last few runs of my experimental data taking use the right version of the code? So I'm going to run this like that. Now you can see we get quite a lot more interesting output here. First of all, it did in fact recompile because I had just removed that error from down here. But now we can see we've got the original values that are coming out from these threads as we saw before, right? The location of the beginning of their subarray and the number of records they're processing. But because we've compiled in this try-lock version of our code, we're also seeing as the thread is getting ready to exit that it has a busy count that is kind of surprisingly high, I guess, right? So thread number 1 tried to lock the global lock and failed to get the lock 567 times. And that's so about 600 times that each of these threads tried to get the lock and didn't get the lock. But in this case, we just went ahead and kept doing useful work, right? We didn't sit around and wait for something else to happen until another thread released that global lock. Now, more interestingly, we didn't ask for the time of that run. So let's do that. Let's add in here time. We don't want to put the time at the very beginning because we don't want to count the number of seconds it took us to compile our code if we did. We only want to time the actual execution. So let's run that. Let me close that out. Now we can see that the real time to execute the fancy new improved try-lock version of the code is only 0.7 of a second, right? So we ran almost 10 times not quite 10 times faster, 8 or 9 times faster than what we did when we were spending a bunch of time twiddling our thumbs waiting for the locks to release themselves. So this was a modest increase in the complexity of the algorithm, But at the end of the day, it resulted in a considerable improvement in the performance because we were eliminating the overhead of waiting for locks. And again, that's a key thing as well. This will come up many times in this semester. In order to go fast, you've got to reduce the amount of extra work that's introduced into the problem by merit of the parallelization. The parallelization is going to give you some increased performance, but it always comes at a cost. There's always some additional overhead. In this case, it's overhead due to locking, and we've come up with a pretty decent solution that helps reduce that to the least amount of time wasted as we can. And that's really evident here when we look at the timing output. So that's just one example of this kind of reduction in parallel overhead that improves our performance, and that's going to continue to be a theme throughout the rest of the course.